Welcome back to Chromatography Experts, hosted by Toso Bioscience, the podcast that discusses all things separation science. I'm your co-host, Corey Meadows, serving as commercial product manager for analytical columns here at Toso Bioscience. And I have the pleasure of being joined with us by a couple of great guests today. First of all, let me introduce my co-host, Landry. Landry?
Hi, my name is Landry Bennett, and I am the Global Technical Sales Specialist here at Toso Bioscience. And I'm proud to introduce our special guest, Tianyu Li. Tianyu, tell us about yourself.
Hi, my name is Tianyu Li, and I'm the application scientist for SCC and TPC instrument at Doso Bioscience.
Tianyu, thanks for joining us today. And I know that you're pretty busy in the lab these days, and I appreciate you taking the time to talk a little bit more about multi-angle light scattering with us. In the previous podcast, Landry graciously joined us and gave us some pretty good insights with respect to some of the more high-level concepts and definitely like a lot of the commercial insights and some of the applications that are emerging in the field. But today is today's podcast. I really want to build more on some of the meat and potatoes of what's going on. Some of the things as a scientist, what do we see? What are the pitfalls we could see? What are the things we need to prepare ourselves to get good MALS or multi-angle light scattering data? So let's just go ahead and get started. So Tianyu, for listeners, first of all, I'm going to start the same way I did last time though, because I still want to hear expert perspectives regardless. And so like from anywhere we can and get our audience up to speed. So first of all, just for listeners who are new to the technique or for maybe people that didn't catch the last podcast, can you briefly explain what MALS is?
MALS, you already talked about, it stands for multi-angle light scattering. It is an analytical technique to measure the absolute molecular weight and the molecular size of the molecule in solution. So the size here we talk about in MALS is radius of gyration.
Okay, so you mentioned something like absolute molecular weight there, right? Like, as a chromatographer, I don't typically qualify molecular weight. So could you just give me a little bit more about what you mean by absolute molecular weight?
Like when we talk about absolute molecular weight, you can think it is the true molecular weight of the sample. Traditionally, people measure molecular weight with the conventional GPC. So we call it relative molecular weight because in this method, you will need a calibration standard for the column calibration. So the measured molecular weight of the sample have the assumption that the sample have the similar behavior as the standards. So the true molecular weight or the absolute molecular weight do not have this assumption. That is the real molecular weight of the sample.
That's really interesting. In fact, there's a lot in there that I actually want to get to and maybe dive into a little bit more as we go through the podcast. But that's actually some really good insight there that kind of helps us frame where the discussion will be going in the future. So, so if I'm thinking about like, what I would need for multi-angle light scattering, what type of instrumentation would I really need to run MALS successfully? And, and how does it typically integrate with things like, say, chromatography or other types of separation techniques?
MALS is always almost used with a separation instrument. For example, SEC-MALS. It means size exclusion chromatography coupled with a multi-angle light scattering detector. For the basics, you will need the concentration detector. That can be RI or UV to provide the concentration measurement. Then we can use concentration to calculate molecular weight. It also depends on what kind of information you want to obtain. People often add viscometer or dynamic light scattering detector with MALS, so you can obtain the confirmation or the branch analysis or more information on the sample.
Okay, so you mentioned like a lot of back-end detectors then, right? Like you mentioned UV visible spectroscopy. You mentioned refractive index, or which is short for RI. You also mentioned viscometry and things like that. So I think, as a former chromatographer, right, like I'm pretty familiar with, like, say, ultraviolet light, and I'm pretty familiar with refractive index and sort of how those things work. Could you just give me a little bit more, maybe to the non-biological side, just about like what viscometry can do for you and what you learn from it?
Yeah, the viscometry can give the sample information on intrinsic viscosity. By analyze the relationship between molecular weight and intrinsic viscosity, we can obtain the confirmation of the sample, which can be seen as the shape of the sample, and also the branching analysis on the sample with a degree of branching or long chain branching, short chain branching, with all kind of the information.
That's really interesting. You bring up a few different detectors. Me personally, I'm certainly familiar with UV vis. I'm certainly familiar with refractive index. But then you mentioned some things about viscometry as well. And as a biological scientist, I hadn't had the opportunity to use that. I was just curious if you could elaborate a little bit more about what we can learn when we implement viscometry.
From this computer, you can obtain intrinsic velocity and RH, hydrodynamic radius of your sample. So with the relationship between intrinsic velocity and molecular weight, you can obtain confirmation of the sample. Of course, by MALS, you obtain Rg. And here you have RH. By the relationship between Rg and RH, you can obtain the confirmation as well. So you can know if your sample is a rod-like shape or random coil shape or a hard sphere.
Okay, so basically there are two different forms of size that we're getting from RG versus RH, right? So that RG, that little g being short for gyration, radius of gyration, H being the smaller one for hydrodynamic radius. Just a little bit more before I go on, like maybe just briefly explain like a little bit of the differences between the two. I know that we've maybe to think of RG as maybe like as a molecule tumbles through space or something like that, but maybe just for our viewers, just kind of explain like what those fine differences are.
Yeah, the radius of gyration is it's more like a mass distribution of the sample. It measures like each atom of a molecule, how its mass distribute around its center.
Okay. So it's really more of one of motion, more or less, right? And then how about RH then?
Yeah, the hydrodynamic radius from its name is actually from diffusion of the sample. So they are RG and RH are measuring totally different things.
So thanks for explaining like, some of the things that we can learn with some of these other detectors that now we can interface with multi-angle light scattering measurements. Uh, but now I kind of want to get into more of the practical part. So, when running chromatography, at least in my experience, right, you're thinking of how do I prepare my mobile phase? How do I prepare my sample? How do I prepare the instrument? How do I prepare the column? I want to know when we're talking about MALS and the associated instrumentation that goes with that, sort of how are you approaching this when you're getting ready to start a MALS experiment? And what are some of the best practices that you implement to help increase the success or the probability of success for a MALS measurement?
Yeah, that's actually the biggest difference from MOS between other like plug-in and play detectors, because MOS is very sensitive to the particle size of the sample, not just the concentration. So we need to keep the chromatography system very clean. In that case, we need to filter the buffer at least twice to make sure there is no particles from the mobile phase. And for the sample, depends on the area. For the polymer area, we always filter our polymer solution before injection. So we are only get the information on the size and on the sample we are interested in. And also, column is also another big impact because column always have some small shedding material. Before introduce MOS detector into the chromatography system, we need to wait for the column be stabilized.
So sometimes when I'm thinking about mobile phase preparation, sometimes I would, filter these in just 0.2 micron filtrated, PES or something like that and call it a day. Is that going to be good enough for like say a MALS type of analysis?
We will suggest to use zero point 0.1 micron instead.
Okay.
Yeah, to make sure to remove all the particles as much as we can from the mobile phase.
Would you, with respect to like say maybe inline filtration, perhaps within plumbing of the instrument, do you have any insights there about maybe what should go in there?
Yeah, like after the pump, we can add another filter to filter the mobile phase all the time in the system.
Okay.
And after column, we can put the post-column filter to remove the column shedding material from the system.
Okay. And then like are there certain materials that are preferred that you're using for these types of analyses as well?
Yeah, it actually depends on different system. If you use organic solvent, for example, THF, the PTFE filter will be the best choice.
Okay.
If you go with polar system, nylon will be a better choice. When we go to the like the bio area, we will use PES filter.
Oh, you bring up a good point too, because some of what we talk about, right? Like with different sizes, right? I don't want to send something that's the size of a vaccine through, say, a 0.2 micron filter is the thing, because now I start to lose things. I start to get things recovery. So always good to kind of know. So at least from what you're telling me, always consider mobile phase composition and also consider the general size before you do your setup on your consumables. Okay, so we have an idea of what sort of detectors. We have an idea of sort of what consumables and some sort of treatment we need to do to get started. If I'm thinking about setting this up in my own lab, though, what sort of resources do I need, or what sort of environment do I need to get up and running?
Mouse do not need a extreme special environment like a clean room. It works with a well-round chromatography lab. So that is just an add-on detector. You can add with your UV or I detector in series or in parallel, depends on your setup.
That's cool. Yeah, and Landry, I know that you've set a few of these up back in the day. Like, do you have any other comments on respect to setup and resources needed to get malls going?
Yeah, I would say, it seems like a really complicated thing, right? But
Uh-huh.
there's almost no additional considerations, right? Yeah, when you use a mass spec, you need a special bench, you need a nitrogen generator, a clean air generator, you need an elephant trunk. You don't need any of this for MALS, right? Unless you're doing something really specific, like using really harsh solvent, like HFIP or something like that.
Okay.
You don't need to have any special considerations to set up MALS. It's not exactly a plug and play detector, as Tiani mentioned earlier, but it's not something that you have to have a, facility built around.
I mean, hey, at the end of the day, if there's different chemistry, then you have to think about a little bit different chemistry and a little bit different physics to accommodate it, right? So,
Yeah.
but that's good to know that I don't need to build out new electricity or do anything like that to get it up and running. So I can, at least from a chromatographer's perspective, I can just kind of see it as it's another box that I can put in line and figure out what the appropriate plumbing would be to get good data.
Yeah, absolutely. Tiani, I want to transition a little bit from facilities, boxes, things like that. I want to drill down into samples, right? And maybe some of the best practices here with MALS. So tell me a little bit what considerations we need to take when it comes to sample preparation before running a MALS experiment.
Yeah, for the sample preparation, still our biggest concern is like the contamination from the dust or the aggregation of the sample, unless the aggregation is a part of the interest for the study. Uh, in most cases, we will filter the sample for polymer area to only target on the designed material. And, and the other part is it's more for chromatography part to make sure your sample do not have any interaction between the column. That MOS can work as good as UV and RI.
Great. Thank you for that. Now, what are some general difficulties you might run into when you maybe run your first MALS experiment or first set of MALS experiments? What are some things that are going to pop up for you?
Yeah, like there we'll have two parts. The first is on the data quality. If the system is not clean, you will see on the like a big noise or the spikes, especially on the extreme low angle, because that is the most sensitive angle on the mouse detector. In that case, we need to keep the system clean before we collect any data. Another part is the data quality itself, because mouse is very sensitive to the size of the particle. Even the concentration is low, if your sample size is extremely large, sometimes your peak might be saturated, but that is not obvious. So you need to zoom in and check the peak tip to make sure the data is in good quality.
Why would we have really high noise? Like, what are some of the issues that someone new to this technique might run into with high noise, like you said, that they may not see with other types of chromatography?
Yeah, it's still from the nature of the detector. It's sensitive to particles, to size. So even one dust particle can give you a spike.
What about gases during the mobile phase, though? Is that like a thing? I know I've only kind of just worked with water for the most part, but I don't know about some of these other solvents because you worked with a lot of polymers before, right? Yeah, so I don't touch a lot of the the harsh solvents, but I'm kind of curious. Like, does that does maybe just are there certain solvents that are easier than others to work with?
Yeah, it's actually depends on the viscosity of the solvent.
Okay.
If the viscosity of solvent is very low, it's very easy to remove the macro air bubbles in the mobile phase. But if the viscosity is high, then the macro bubble will also scatter the light all the way, like in all the angles. Then you lost your quality of the data.
And then these things can contribute to that spiking or equilibration and things like that that you were talking about earlier.
Okay, so we've got some things that might pop up for us. Tell me a little bit about what we can do to, maintain an instrument in a clean state or restore an instrument to a clean state if it does get dirty.
Yeah, like for using the mouse, we need to make the first step right. That is, it's actually very easy. Filter the buffer. After the buffer system is good, then we need to stabilize the column. For example, 5 or 10 column volumes depends on the different columns. After the system is clean and stable, then we introduce the MOS detector. In most cases, you will have a very good data. Unfortunately, if your device go to a dirty environment with the introduction of the particles or contaminations, we need to clean the detector in a controlled way. It means first clean the chromatography system with the column. After the chromatography system is clean, then we connect the MOS back, clean the MOS detector with the different solvents depends on what kind of contamination you are dealing with.
Is there any way to determine how clean your system is prior to putting a MALS detector on? Like, I'm thinking about particle shedding, for example, right? You mentioned this earlier. These particles are not UV active, right? So how can we, is there any other way to see what we're looking at here?
Uh, it will be a little bit challenge because R and UV, they are not sensitive to the size. So we generally recommend to keep your system stable for at least 5 column volumes. In that case, if you already filtered your mobile phase, the particles will from your column. After your column stabilize, there should have much less particles from the column. Then your mouse should be clean.
Yeah, and so, I think we've kind of touched on a little bit there, right? But like if I'm thinking about how to keep a malls that, humming, so to speak. In other words, like are there any best practices that we maybe haven't covered that would maybe help us maintain that instrument performance or the detector performance?
The most important thing is filter the mobile phase. Then the system go in a good conditions. And also we can monitor the pressure, the baseline noise, the drifting all the time. If there is any change, we also recommend to clean the detector regularly. For example, half a year to clean the detector. If you use it in aqueous, we can use magic buffer to clean all the detectors thoroughly.
And what's that again, just for our audience?
Yeah, the magic buffer.
Yeah.
Yeah, that is traditional used cleaner for the HPLC. It's a 1:1:1:1 ratio of the isonitrile, methanol, water, and isopropanol. So it can clean your HPLC and MOS very effectively.
Yeah, I remember those days if you've seen those things. So basically still like a lot of LC related cleanings and things like that for going there.
One thing I would add too is that for aqueous mobile phase, this isn't really a problem for polymers with organic mobile
Mhm.
phases, but in aqueous mobile phases, these salty buffers, we get bacteria growth a lot.
Yeah.
So one thing that we actually recommend a lot is to add, azide to a mobile phase
Mhm.
to ward against bacteria growth happening in your mobile phase bottle or even in the lines in the system.
I'm glad that you brought that up too, because we're certainly if you're able to use azote, it's a fantastic way to arrest growth in your columns as well. But just a little bit as we bring this up with organic solvents. If you're using organic solvent, right, but you've been using like say a salty buffer, make sure you transition just from the salty buffer to the water to the mixed organic solvent, because if you put that mixed organic solvent on there with that salty buffer, well, now it's not a MALS problem. Now it's a parts problem. So glad we brought that up. But just the chromatographer in me wants to kind of just do that public service announcement before we go on with the MALS. Now that we have an idea of how to get good data, what are the most important considerations that say an end user needs to keep in mind when they're either working up that MALS data or when they're interpreting that MALS data?
Yeah. For the MOS data, one important thing we need to keep in mind is the model fitting. Because on different sample with different conformation, you may need to apply different models. For example, Zing, Dubai, or Berry models, and so on. So you need to check if the model fitting looks good or it's like have physical meanings.
So, we mentioned a lot about models and, I'm just thinking to myself if if I have raw data that could be plot in some sort of linear relationships, there's a lot of ways to fit data, right? How do we know which model to use and when to use that?
Depends on the different sample conformations. The model can be found in the literature. For example, for random coil shape with a size smaller than 50 nanometers, Zimplot is a good choice. Uh, if you have a detector with a low angle can go to around 10 degree, then you can have a low assumption or a model-free analysis for a direct molecular measurement.
So I can do an assumption or model free measurement if I have a low enough angle is what you just said.
Yes.
Interesting. Interesting. So what about challenges that may be related to like say data analysis or software? Or is there any, any insights or anything that you've kind of noticed when it comes to working up your data?
The most challenge is still on the model fitting, especially for the new users. That will be a big learning curve to learn different models and with like especially for unknown samples. When you do not know your confirmation of your sample, how do you choose a model?
Yeah. So and then just finally, like what sort of best practices would you recommend to someone who uh wants to get reliable performance from malls?
Yeah, we can go from the system preparation to the data analysis. From the system, the biggest important thing is cleanness of the chromatography system. So filtrate your buffer. If filtration of the sample can be done, also filtrate your sample. Then before injection, we need to double check the baselines, not only for the MALS, but also RI and UV. The concentration detection is also important on the MALS analysis. Then we go to data analysis. To obtain molecular weight, we need to know concentration information on the sample. There is two cases. First, you know your concentration of your sample. Then you can calculate DNDC or UV extension coefficient, depends on the detectors. You can compare your values with the literature values to make sure your concentration during the sample preparation is correct. The next direction is you know the sample DNDC or the ADC. Then you can have the calculated concentration and recovery.
If I don't have that, is there like an approach to where I can get that particular value, right? Because, sometimes that's not exactly known up front.
Yes, for the DNDC, it's easy. It can be calculated from the uh, DNDC measurement from RI detector. You only need to do a gradient of the concentration and measure its RI response. The slope is DNDC. For DADC, it can be done similarly, but it can also be calculated theoretically if you are working on protein or DNA kind of the samples.
So I know I can get like an extinction coefficient from like, say, DNA or protein. Is that related to that particular parameter?
Yes.
How?
Like the UV extension coefficient divided by molecular weight is actually DDC.
Yeah, that's what I was looking for. It's like, okay, because there's some different biology terms and different ways of that we kind of think of things. So it's good to know that it's actually kind of in there, or we can at least maybe for a starting point kind of calculate that, and then perhaps divide by theoretical molecular weight as a starting point. And then in principle, I guess that could be kind of used consistently for analysis as you go forward.
Yeah. Like there is also available tools online. You can just put your sequence of the sample, then it can give you the DDC values.
Okay.
Thank you, Tiani, for joining us today. And thank you, Corey, for hosting this podcast with me. Thank you for joining us on this edition of the Chromatography Experts podcast. I hope you learned a lot about implementing MALS detectors and how we can do that safely and how we can do that reproducibly. Subscribe for more chromatography insights, and we'll see you on the next episode.